All right, welcome back, everyone, to the deep dive. We're diving into a super interesting paper today, all about data.
Yeah, this one is fascinating.
It is, right? So it's called Data Scaling Laws for End-to-End Autonomous Driving.
Catchy.
It is catchy. You know, sometimes these titles are just like alphabet soup. But this one, I think, gets right to the point, and it's from NVIDIA and a bunch of their collaborators from various universities. So I guess for the folks tuning in for the first time, you need the quick summary, the PLDR, if you will.
The elevator pitch.
Yeah, the elevator pitch. Basically, this paper is saying when it comes to self-driving cars, and particularly the systems that go straight from the sensors to the actions the car takes.
The end-to-end approach.
Exactly, that end-to-end approach. Just having more data doesn't automatically mean a better system.
Right, it's not just about the quantity of data.
No. You also need to think about how powerful your model is. How much it can actually learn from all that data.
It's capacity.
Capacity, exactly. And this paper, they didn't mess around. They tested this idea across a huge range of data. I mean, we're talking from 16 hours of driving data all the way up to over 8,000.
Yeah, that's a pretty impressive scale.
It's massive, right? And they didn't just look at, theoretical metrics. They actually put these models into a realistic simulation.
Closed loop testing, seeing how they handle a virtual world.
Exactly, closed loop. And the big finding, well, to get the best performance, you've got to scale both your data and your model size the right way.
Yeah, it's like a recipe. You need the right ingredients in the right proportions.
Perfect analogy. So for those of you deep in the world of autonomous vehicles or even just keeping an eye on the field, this paper is tackling a really fundamental problem.
Absolutely. It's all about figuring out the best way to use the data we have to make these systems better.
Right. And traditionally, a lot of autonomous vehicle systems, they kind of break down the problem into these separate modules. You've got perception, prediction, and then planning.
It's the classic approach.
It is. But the end-to-end idea, it tries to do things a bit differently. It wants to learn the whole driving task in one go. So from the sensor data straight to the controls.
And the hope is, if you feed these systems enough data, they can pick up all those subtle driving behaviors without us having to program every single rule.
Right, it's like learning by doing rather than by instruction.
Exactly. And what this deep dive does, it looks at how much data you actually need and what kind of models you need to make that work.
Okay, so for our listeners who are more familiar with that kind of classic modular approach, can you break down what the limitations are that end-to-end is trying to solve?
Sure. Imagine it like a relay race, right? You've got each runner with a specific task, but every time they hand off the baton, there's a chance for things to go wrong. Information can get lost, or there can be a fumble.
And in the modular system, the baton is the information, right? About the environment, the objects, the predictions.
Precisely. So your perception system, it might have a really good understanding of what's happening around the car, but only some of that gets passed on to the prediction module, and then even less to the planning module.
So it's like a game of telephone where the message gets distorted with each retelling.
Exactly. And on top of that, you've got all these separate systems, each one pretty complex, all needing their own processing power.
It gets computationally expensive.
It does. But maybe even more important is that if you have even a small mistake early on, say an object detection, that error, it can snowball. As it gets passed down the line through prediction and planning, it can get amplified, potentially leading to a big driving error.
That's a scary thought.
Yeah.
So the end-to-end idea, it's about cutting out those middlemen. You take all the raw sensory data, camera images, LiDAR, whatever you're using, and you feed that directly into the system. And what you want out the other end are the commands for the car. Steering, acceleration, braking, the whole deal.
It's like teaching a kid to ride a bike, not by explaining physics and balance, but by just letting them try and fall until they get it.
Learning by experience.
Exactly. And the biggest advantage here is that you can, in theory, optimize the whole system together. Instead of tweaking each module separately, the entire network is learning to drive safely and efficiently as one unit.
So it's more holistic.
It is. This lets the system pick up those complex relationships in the data that we might miss if we're trying to hand design everything. But the question this paper is really wrestling with is how data plays into this. If we just give these systems more and more data, will they just keep getting better?
That's the core of their investigation into these so-called scaling laws. Now, they make a connection to something we've seen in natural language processing, or NLP.
Yeah.
Can you explain that for our listeners who might not be as familiar with that field?
Sure. So in NLP, they've found these pretty predictable relationships between how much data you use to train your models, how big those models are, and how well they perform on tasks like, say, generating text or translating languages.
So bigger models and more data usually mean better performance.
Generally, yeah. And often it follows this power law relationship. So as you increase either the data or the model size, the performance keeps improving, but at a predictable rate.
That's handy.
It is. It helps guide research and development. Now, in autonomous driving, we haven't had the same level of analysis on such a large scale. The main reason, we haven't had access to these huge publicly available data sets.
Because getting all that driving data and then labeling it, that's got to be expensive and time-consuming.
Hugely. So until now, there's been this big question mark about whether these same scaling laws would even apply to self-driving cars. And if they did, what the trade-offs would be between the data and the model size.
So this paper, this is kind of groundbreaking in that sense.
It is. It's a big step towards answering those questions.
So the folks at NVIDIA, they took on this challenge.
They did.
What kind of end-to-end system did they use, and what was this huge data set they put together?
Okay, so they kept the driving setup relatively simple. They went with imitation learning. Basically, the model is trying to learn to copy what a human driver would do based on the data it's given.
Like an apprentice watching a master.
Exactly. And for their main input, they used images from 3 cameras, wide-angle RGB cameras covering the front, left, and right views.
Okay.
And the goal of the model: to predict the trajectory of the car, a sequence of future positions, where the car will be in the next few seconds.
Got it.
Now, the data set itself is pretty remarkable. It's an internal data set they have, ranging from just 16 hours of driving all the way up to a whopping 800 and 192 hours. That's over a year of continuous driving.
That's a lot of driving.
It is. And to put it in perspective, they point out that even those famous public data sets like New Scenes or the Lyft Level 5 data set, they're way smaller, like orders of magnitude smaller.
Wow. So what did they use to measure how well these models were doing?
For their initial tests, they used standard open loop metrics, basically comparing the trajectory the model predicted to the actual trajectory the car took in the data.
Okay.
But here's the important part. They also tested these models in a closed-loop simulator.
You mean they actually let the models drive a virtual car?
Exactly. They used NVIDIA Drive Sima, which is a super realistic simulator. This let them see how well the models could handle the dynamic world, react to things, not just predict what a human would do.
That's a much tougher test.
Oh, absolutely. And they used something called the mean distance between failures, or MDBF, as their main metric to see how robust the driving was.
So what were the big takeaways from all of this? What did this research really contribute?
Well, for one thing, it's the most complete and systematic look at data scaling laws in end-to-end autonomous driving we've ever seen. They really mapped out these trends across different driving actions and different model sizes.
So that in itself is a contribution.
Huge. They also dug into the practical challenges of training these giant models on these massive data sets, and they even came up with a new training schedule to handle it all.
Clever.
Right. They also explored how much more data you'd need to squeeze out even more performance by fitting different scaling law estimators to their results. And of course, they didn't just stop at the theoretical stuff. They went and put those models through their paces in the simulator using that MDBF metric to see how they'd handle the real world, or at least a pretty darn good simulation of it.
Okay, let's talk about that data set a bit more. 8,000 hours of driving data. That's an unbelievable amount. What did they do to make sure that data was good quality and that it was actually representative for this kind of analysis?
Yeah, 8,000 hours is mind-blowing. That's over 400,000 kilometers driven across over 10 different countries. And they didn't just use any old data. They were very specific.
In what way?
Well, their sensor input, it was all from those 3 wide-angle cameras we talked about, capturing images at a resolution of 734 by 270 and at a rate of 10 frames per second.
Pretty standard stuff.
Yeah. Then they took the car's actual path, the trajectory, and they sampled that at 5 times per second. And to create the labels for the model, they looked 3 seconds into the future from each of those points.
So the model's trying to predict where the car will be in the next 3 seconds.
Exactly. And they created a bunch of different training data sets, each one twice the size of the one before it. They started with a tiny 16-hour dataset and went all the way up to that massive 892-hour dataset. And importantly, each smaller dataset was included in the bigger one.
So they could really isolate the effects of scaling up the data.
Precisely. They also made sure to point out how much bigger their dataset was compared to those public benchmarks, like just to emphasize the scale of what they were working with.
It's important to put things in context.
Yeah.
Okay, so with all that driving data from different places, how did they avoid data leakage? Making sure the model wasn't accidentally seeing data from the test set during training. They mentioned something called geofencing, right?
Yeah, geofencing was their solution. And it's super important, right? Because if your model has already seen the data it's being tested on, your results are meaningless.
Totally.
So they basically divided their entire data set based on where the data was collected. They focused mainly on Europe and North America, making absolutely sure that the data used for training, validation, and the final test, it all came from completely separate areas, no overlap at all.
So how did they do that?
They used this clever graph-based clustering method. Imagine each driving session and the little H3 cells it covers as a point on a graph. By finding the connected components within that graph, they could group together sessions that happened close to each other, forming these distinct geographical clusters.
I see. So a model trained on data from one cluster would never have seen data from another cluster during training.
Precisely. That way, they were completely confident that their model wasn't getting any sneak peeks at the test data.
That's really thorough. Yeah. What about the actual driving scenarios? Did they make sure that the types of roads and the conditions were similar across all the different data set sizes?
Oh, absolutely. They were very careful to keep what they call the operational design domain consistent. So things like the type of road, was it a highway, a city street, a residential area, or a rural road? And the lighting conditions. Was it daytime, night, twilight?
Yeah.
And even the road surface, dry, wet, snow, or ice.
Wow, they thought of everything.
They did, and they made sure that the proportions of all these different conditions stayed pretty much the same across all their data sets. So whether you were looking at the 16-hour data set or the 892-hour data set, the mix of scenarios was pretty much identical.
Smart. So any performance differences they saw, you could be confident that they were actually due to the amount of data or the model size, not because the model was seeing different kinds of driving situations.
Exactly. It's all about controlling those variables.
Okay, so they've got all this driving data, but they also need to label it. Specifically, they need to know what the car is doing at each moment. Is it turning, changing lanes, just keeping straight? How did they handle that at this scale?
That's a great question. It's a lot of data to label. So they came up with a way to automatically figure out what the driving actions were based on the car's trajectory and map data. They used things like lane boundaries and road geometry to determine if the car was at an intersection, meaning it was probably turning, or if it was moving sideways into another lane, indicating a lane change.
Clever. So they didn't have to manually label everything by hand?
Nope. They did have to deal with some inconsistencies in the localization data, though. Sometimes the GPS or other sensors can be a little noisy.
Yeah, makes sense.
So they actually extended a data format called Traj data to handle those issues. It's all about making sure the labels are accurate and consistent, even with a little bit of noise in the raw data.
And how did they finally decide on a single label for each moment in time?
They used a majority voting system. Basically, they looked at several snapshots of the map data close together in time, and whatever action was most common, that's what they labeled it as.
Makes sense. So what was the final breakdown?
As you might expect, most of the data was just lane keeping, about 92%. Turns were about 5%, and lane changes were about 3%.
Oh.
Which makes sense, right? Most of the time when you're driving, you're just staying in your lane.
Absolutely. Okay, let's move on to the model itself. It sounds like they kept things pretty simple in terms of the design to really focus on the data scaling.
Right. They wanted to isolate those variables. So their model has two main parts. The first part is the perception module. It takes the camera images and extracts all the important features. And the second part is the prediction module. It takes those features and uses them to predict the future path of the car.
So perception is about understanding the current situation.
Yes. And prediction is about anticipating what will happen next.
Got it. And they specifically chose not to use past driving history as an input. Why was that?
They wanted to force the model to rely mostly on the current visual information, what it was seeing right then and there.
Interesting approach. So what kind of neural network did they use for the perception module?
They used something called ResNet, which is a pretty popular architecture for image processing. They actually experimented with two different versions, ResNet 18 and ResNet 50. The numbers refer to the number of layers in the network. So ResNet 50 is a bit more complex, has more capacity to learn.
And how did they handle the input from the 3 cameras?
Well, each camera image was processed separately by the ResNet encoder. This created a separate feature vector for each camera view. But to get a full picture, you need to combine those views. So they use something called cross-attention for that.
Cross-attention, that sounds familiar. Can you remind us how that works?
It's like a way for the model to focus on the most important information from each camera view and then blend them together intelligently. So the features from the front camera act as the query, like what are we looking for? And the features from the left and right cameras, they're the keys and values. They tell the model what's out there and how important it is.
Gotcha. And this allows the model to get a full 360-degree view of the environment.
Exactly.
Cool. So once you have this combined information from all the cameras, how does the prediction module actually turn that into a predicted driving trajectory?
Good question. So it takes those combined image features, but it also needs to know what the driver intends to do. Like, are they planning to turn, change lanes, or just keep going straight?
Right.
So they encode that information into a separate feature vector, along with the current speed, acceleration, and jerk of the car.
So the model knows what the car is currently doing and what the driver wants to do.
Yep. And they feed all this information into another cross-attention layer, which blends everything together. And the output of that goes into a final MLP, a multi-layer perceptron.
And that MLP spits out the predicted trajectory.
You got it. A sequence of 15 points representing where the model thinks the car will be in the next 3 seconds.
Okay, so we've talked about the data and the model architecture, but actually training these massive models on such huge data sets, I imagine that presents its own challenges.
It definitely does. Training these models is a computationally intensive process, and they needed to come up with a way to do it efficiently, especially with those larger data sets. So they introduced a custom learning rate schedule.
Can you break that down for us?
Sure. So they used a technique called cosine annealing. Basically, the learning rate, which controls how quickly the model learns, it gradually decreases over time. This helps the model converge, find the best solution without jumping around too much.
Right.
But the typical way to do this involves setting a fixed number of training epochs beforehand. And they found that this was inefficient.
Inefficient in what way?
Well, if you train for too few epochs, the model might not learn everything it can. But if you train for too many, you risk overfitting, where the model gets really good at the training data, but doesn't generalize well to new situations.
So it's like studying too hard for a test and then forgetting everything the next day?
Exactly. So they needed a more flexible approach. Instead of fixing the number of epochs, they came up with this linearly decreasing compute schedule. Basically, the larger the data set, the longer they trained it for, but in a very controlled way.
So they can make sure that each model, regardless of the data set size, got enough training without overdoing it.
Exactly. It's all about finding that sweet spot. And their approach also gave them a good way to figure out the cycle length for their cosine annealing schedule.
Very cool. Now, to actually figure out the relationship between the amount of data and the performance of the models, they use something called scaling law estimators. What are those exactly, and how did they choose the right ones for their research?
Okay, so scaling law estimators are basically mathematical equations that try to describe how the performance of a model changes as you give it more data.
So like a formula that predicts how much better the model will get with, say, twice as much data.
Exactly. They looked at 4 different estimators, each a bit more complex than the last. The simplest one was just a basic power law, but the others had more parameters to capture those subtle details in the scaling behavior.
Okay.
Now, their goal wasn't just to find an estimator that fit their current data really well, but also one that could predict performance on even larger data sets they hadn't even tested yet.
So one that could extrapolate beyond what they'd already seen.
Exactly. To do this, they trained their models on those smaller data sets up to 512 hours, and then used the performance results to fit each estimator. Then they tested how well each estimator predicted the performance on those larger data sets, the 10,000 24-hour and 2048-hour ones.
Smart. So it was like a little prediction challenge for the estimators.
Exactly. And they used the mean squared error of the final displacement error as their score.
Okay, let's jump into the results. What did they find when they evaluated their models in that open loop setting, where the model is just predicting trajectories based on the data? Let's start with the smaller model, the ResNet 18, with just a single front-facing camera.
Okay, so when they looked at how well those scaling law estimators could predict the performance on those really big data sets, 496 hours and 892 hours, based on the smaller ones, they found that one estimator called M2, it did the best overall job.
M2, got it.
Yeah, and it was particularly good at predicting the performance for lane keeping and lane changing. For turning, a slightly different estimator, M3, was a bit more accurate. But they did notice something interesting.
What's that?
These estimators, they tended to be a bit too optimistic, especially for those combined actions, lane keeping and turning. For lane changing, they were closer to the mark.
So they were overestimating how well the models would do with more data.
Yeah, a little bit. But when they looked at how performance scaled across those different driving actions, lane keeping, turning, lane changing, they normalized the final displacement error so they could compare them directly. And what they found was pretty cool. Lane keeping, it improved the fastest as they added more data. Lane changing, it improved, but not as quickly. And turning, it kind of hit a ceiling after they got to that 800 and 192 hour data set.
So some tasks benefit more from data than others.
It seems that way, and it probably has a lot to do with how complex the task is and how often it comes up in the data.
Yeah, that makes sense. Now, they used a few different metrics to evaluate the models, right? Like the average displacement error, final displacement error, and miss rate. Did those all tell the same story about how performance scaled with data?
They did. They found the best scaling law estimator for each of those metrics, and it turned out to be M2 again for all three.
M2 is really pulling its weight.
It is. And the cool thing is, all three metrics scaled in a pretty similar way as they added more data. They had similar scaling exponents, which means they improved at roughly the same rate. However, the miss rate, which tells you how often the model predicts a final position that's way off from the real one, that one dropped more dramatically than the others.
Why is that?
Well, the miss rate, it's based on a threshold, in their case, 2 meters. So once the model's predictions get consistently within that 2-meter margin of error, the miss rate drops really quickly.
Gotcha. So they've got this massive data set, 800 and 182 hours. But did they try to extrapolate those scaling laws even further? What would it take to get even a tiny bit more performance?
They did, and the results were pretty telling. It turns out to get a 1% improvement in the final displacement error beyond what they achieved with those 800 and 192 hours, they'd need another 4,000 hours of data.
Okay, that's a lot, but maybe doable.
Yeah, but for a 3% improvement, they'd need about 29,000 more hours. And for a 5% improvement, hold on to your hats, they need a whopping 273,000 hours.
That's more data than they already have.
Way more. And it really highlights the fact that just collecting more and more data, it has diminishing returns. Eventually, the improvements you get are so small, it's just not practical.
So that brings us to the model itself. They also did experiments with the larger model, the Resonant 50, right? Did that change things?
Oh, it did. Remember how we talked about model capacity, how much a model can actually learn?
Mm-hmm.
Well, they had this idea that maybe the Resonant 18, it just wasn't big enough to really benefit from those huge data sets.
Like it was being held back by its own limitations.
Precisely. So they switched to the Resonant 50, which has way more parameters, more capacity to learn.
Yeah.
The results were pretty dramatic. With the Resonant 50, they saw much better scaling across all the different driving scenarios. In fact, it was able to achieve similar performance to the Resonant 18, but with much less data.
How much less?
In some cases, it needed only 63% to 78% of the data to get the same results. For example, for overall driving performance, the Resonant 50 trained on about 3,000 hours of data, did just as well as the Resonant 18 trained on the full 8,192 hours.
That's a huge difference. So the takeaway here is that it's not just about the data. You need a model that's powerful enough to actually learn from it.
Exactly. You need both ingredients, data, and model capacity in the right balance.
Okay, what about adding more sensors? They also experimented with using all 3 cameras instead of just the one. Right.
They did. But interestingly, using 3 cameras with the Resonant 18, it didn't actually make that much of a difference in the overall performance.
So that's surprising?
Yeah, but they think it's because most of their data was focused on lane keeping, where the front camera is probably all you need. However, when they looked specifically at lane changing and turning, they did see a small improvement, about 4 or 5%, with the 3 cameras on that 512-hour data set.
So for those more complex maneuvers, having more viewpoints does help.
It seems that way, but for simpler tasks, just adding more cameras might not be the answer.
Okay, now for the real test. They took these models, which looked good in those open-loop evaluations, and put them into the closed-loop simulator. How did they do when they had to actually drive in a more realistic virtual environment?
this is where things get really interesting. They found that even though the open-loop metrics kept improving with more data, the actual driving performance in the simulator, measured by that MDBF, it only got better up to a certain point.
What point was that?
Around 256 hours of data. After that, the MDBF kind of plateaued. It stayed at about 1 kilometer, even with all that extra data.
So even though the models were getting better at predicting what a human would do, they weren't necessarily becoming better drivers.
Exactly, and it's a crucial point. They even tried things like image augmentation to make the simulated world more like the real world.
To bridge the gap between simulation and reality.
Precisely. And they tried making the model's brain bigger, increasing the capacity of the planner head. But nothing really worked. They still hit that performance ceiling in the closed-loop tests.
That's fascinating. So why do you think there's this disconnect between the open-loop and closed-loop results?
They think a big part of it is what's called covariate shift. Basically, the model learns to imitate human driving on the data it's given, but the real world, even a simulated one, it throws curveballs.
Unforeseen situations that the model hasn't been trained on?
Exactly. And when those happen, the model doesn't know what to do. It hasn't learned to generalize, so it might make bad decisions, and that leads to a lower MDBF.
So it's not enough to just imitate. The model needs to understand the principles behind driving to be able to handle those unexpected situations.
Precisely. The paper suggests a few things to tackle this. They mention techniques like Dagger, where you basically train the model on its own mistakes, and adding extra learning tasks to help the model develop a more robust understanding of driving.
Sounds promising.
It does. And they also suggest moving towards more closed-loop training, where the model is specifically trained to optimize for driving outcomes, not just imitate actions.
That makes sense. So it's not just about more data, it's about the right kind of data and the right kind of training. This research really opens up a lot of interesting avenues for the future of end-to-end autonomous driving. What were some of the areas the authors themselves suggested for further exploration?
They had a few really interesting ideas. One is to move beyond just using cameras and incorporate other kinds of sensors like LiDAR and radar.
To get a richer picture of the environment.
Exactly. Yeah. They also suggested looking at how to incorporate temporal information into the model, being able to understand how the scene changes over time and to better model the behavior of other cars and pedestrians.
Makes sense.
And they also think that using even more accurate action labels, maybe even getting humans to label them, could lead to better scaling laws. And finally, they want to apply this type of analysis to those more advanced end-to-end models that are out there.
To see if these findings hold up with different architectures.
Precisely.
Fantastic. So let's wrap this up. What are the key takeaways for our listeners?
I think the big one is that to build really high-performing self-driving systems, you can't just focus on data alone. You need to scale both your data and your model together in a balanced way.
It's a two-pronged approach.
Exactly. And they showed very clearly that a larger model, like that ResNet 50, could really make use of all that data. They also found that different driving tasks improve at different rates, with simpler tasks like lane keeping getting better faster than harder things like lane changing.
So even within the driving task, there are nuances.
Definitely. And they also found that adding more cameras didn't always make things better, at least for those simpler tasks. And I think the biggest takeaway is that gap between what the models can do in the lab, those open loop tests, and what they can do in the real world, or even a good simulation of it.
That gap is still very real.
It is. And it suggests that just imitating human driving, even with tons of data, it might not be enough to get us to truly reliable self-driving cars.
So for our listeners out there, the researchers, the engineers, the people pushing the boundaries of AI and robotics, given everything we've discussed, where do you think the focus should be? What are the most important things to invest in if we want to accelerate the development of safe and reliable autonomous driving?
That's the million-dollar question, isn't it? Should we be putting more effort into collecting even more data, building even bigger and more complex models, or maybe focusing on making those simulations even more realistic?
Or maybe a combination of all three?
Probably. There's no easy answer, but these are the kinds of questions we need to be asking. And as we keep pushing the limits of what's possible with AI, it's exciting to think about what we might discover along the way.
Absolutely. So for those of you who want to dive deeper, the paper is called Data Scaling Laws for End-to-End Autonomous Driving by Noman and their colleagues. Definitely check it out, explore their methods and results, and see how it relates to your own work. And we always love to hear your thoughts, so feel free to share your insights and continue the conversation.
Yeah, let us know what you think.
Thanks for joining us on the Deep Dive.
See you next time.